Modern naval vessels are crucial to military supremacy and cost upwards of billions of dollars per ship. They are equipped with cutting-edge active and passive defenses, but are still vulnerable to a number of threats. When entering enemy waters, ships are at a high risk of damage from explosions of enemy mines. These mines impinge high-amplitude shock on a ship's hull, which is attenuated by the displacement of internal structural members. This can cause members to plastically deform or fail, but usually will cause most damage elsewhere by destroying internal equipment. Thus, it is important to explore new methods to internally attenuate this shock to create more robust vessels. Sponsored by Dr. John Melcher of the Johns Hopkins Applied Physics Lab, our undergraduate Capstone team at the Pennsylvania State University sought out to solve this problem. To do this, we examined the efficacy of constrained particle dampers in reducing the amplitude of beam vibrations from large shock inputs. Constrained particle dampers utilize collisions between particles and container walls and interparticle friction to dissipate energy. Unlike traditional dashpot dampers, constrained particle dampers require large acceleration amplitudes to provide significant damping, as this will cause enough excitation for collisions to occur in addition to friction. They also behave extremely nonlinearly due to the interactions of the many particles. To test this at a fundamental level, the team designed simple, customizable dampers to be attached to a rectangular bar. This design allowed us to examine several parameters: particle size, particle fill rate, mass ratio, and the effect of cells. We created dampers of two different lengths from aluminum square tube and used slot-fitted sheet metal lattices to test the effect of cells. 1/4 and 1/8 inch balls as well as sand were tested as fillers. The dampers were attached to a clamped aluminum bar and excited by an impact hammer. 3 accelerometers along the beam's length captured data which we exported to MATLAB and compared to a baseline between tests to guide our experiments. We then used MATLAB's signal processing toolbox to create models and do modal analysis to quantify damping ratios. Through our analysis of the data, we found that the 3-inch damper with 1/8 inch balls at 95% fill and no lattice produced the best results. Though it increased the mass of the beam system by 29%, it increased the estimated damping of the beam by 136% and decreased the maximum amplitude of acceleration by about 60%. Overall, we concluded that constrained particles are highly promising in the field of structural shock absorption. For a reasonable increase in mass, they offer a significant increase in energy dissipation. In the future, our team would like to test constrained particle dampers on more practical structural members like I-beams to advance this exciting new technology.